Hello and welcome to our webinar. Our topic today is wall bracing in high seismic regions. This is part 4 of our wall bracing series. If you haven't watched parts 1 through 3, please check them out. We'll briefly touch on a couple of topics from these webinars, but some of the discussion may be confusing if you've not watched the earlier modules. They are available on our website for on-demand viewing at apawood.org. My name is Karen Beebe. I am the Western Region Manager for APA, the Engineered Wood Association's Field Services Division, and I will serve as the moderator for this session. APA is a nonprofit trade association representing manufacturers of a variety of common structural engineered wood products. In addition to quality verification and product testing, APA conducts research to improve engineered wood products and the systems where they are used. We also educate users and specifiers on the product's intended use and potential applications. Before we start today's webinar, I need to cover some housekeeping details. The presentation will last around 80 minutes, and then we'll also have Q&A at the end for as much time as we have available. I'd also like to note that today's program is approved for AIA and ICC continuing education credits. After the conclusion of the webinar, you can download your customized certificates of completion. Your feedback is important to us. Please note the QR code in the center of your screen. If you have a smartphone handy, you can open it up to the camera app, point it at that QR code, and that'll take you to a link to today's survey. Your feedback helps us improve these sessions and guides us in what we should provide for our audiences. Today we have two speakers, Alita Dean and Larry Owning, who are both engineered wood specialists with APA's Field Services Division. In their role, they work with designers, building officials, and builders on the various engineered wood products that are used in buildings today and consult on engineered wood use in construction applications. A few notes on their backgrounds. I'll begin with our first presenter today, who is Alita Dean. She's based in California and she supports the Southwest, including California, Arizona, and Nevada. Prior to joining APA, Alita worked as a structural engineer for 9 years, designing buildings of all types, including schools, commercial, construction, and residential. Alita is a professional engineer licensed in the state of California. She has a Bachelor's of Science in Architectural Engineering from Cal Poly San Luis Obispo. Our second speaker is Larry Owning. He is based in Oregon and supports the Pacific Northwest, including Oregon, Washington, and Idaho. Prior to joining APA, Larry was the General Sales Manager for Louisiana Pacific Corporation, where he managed a team responsible for the sales of all LP products in Western Canada and Northwest United States. Before LP, Larry had 20 years of experience as a commercial construction manager, where he built over 60 significant commercial projects of different types, many of which were primarily wood construction. Larry has a bachelor's and master's degree in civil engineering structures from Washington State University. Larry is a professional engineer in the state of California. For those of you just joining us, welcome to our webinar, Wall Bracing 4, Wall Bracing in High Seismic Regions. I will now turn the microphone over to our first speaker, Alita Dean.
Thanks, Karen, and welcome everyone. Today, our learning objectives are going to include a basic understanding of the IRC versus IBC design, but we're going to focus on the limitations and possibilities when designing with the residential code, specifically in high seismic regions. During today's webinar, we're going to work from left to right through the topics shown on these tabs. Now, assuming you've watched module 1 through 3, we're going to skip over load path today and hop right into limits, since these are going to change when you're designing for seismic loads. Wall bracing or shear walls are a primary way designers resist lateral loads. Now, some people may use these terms interchangeably, but we're going to differentiate between the two. Across the country, most homes are built in accordance with the prescriptive provisions of the residential code. This means that the homes are not engineered. To use prescriptive construction, the designer is limited to a maximum building size, a maximum wall height, and normal lateral loads. Now, normal lateral loads are considered to be ultimate wind speeds less than 140 miles per hour, and they exclude high seismic activity on loose soils. Braced wall panels, or BWPs for short, are prescriptive elements of a structure that resist those lateral loads. If the house design exceeds the prescriptive limitations of the code, the house needs to get engineered. An engineered design is going to use shear walls to resist those lateral loads. Shear walls are engineered elements of buildings and require calculations and a design professional. So that's braced wall panels, or BWPs, get used with the IRC. Shear walls are getting used with the IBC and an engineer. The residential code doesn't apply to every building or even every residential building. So we're going to review a couple of the basic IRC scope limitations. The provisions are based on the seismic design category, or SDC for short, as well as whether the structure is a townhome or a detached one or two family dwelling. The seismic provisions in the residential code are going to apply to townhomes in seismic design category C, D0, D1, and D2, as well as detached one and two family dwellings in seismic design category D0, D1, and D2. This chart illustrates the seismic provisions in the residential code. The upper area shown in blue contains the buildings and seismic design categories that are exempt from the seismic provisions. Seismic provisions will only apply to buildings in the seismic design categories shown in the lower area that's colored in red. If you're looking for the seismic design category for your project, you can consult the residential code map in section R301.2, or you can check with your local jurisdiction. You may have noticed on the previous slide that unlike detached homes, townhomes in seismic design category C require seismic design. So the residential code is defining townhomes as 3 or more attached units. That means that the IRC is not requiring a duplex in seismic design category C to meet the seismic provisions. Each townhome living space also needs to be stacked vertically, so nobody should have any upstairs or downstairs neighbors. And each townhome also needs to have at least 2 exterior sides open, just like in the 2 examples shown here. This building configuration is not going to meet that IRC definition of a townhouse. It's meeting the first 2 requirements. So we have over 3 units, and each unit extends from the foundation to the roof, but the middle 2 units are not open on 2 sides. So this building requires the use of the IBC or another code standard for design. You cannot use the IRC for this building. Because the IRC is prescriptive, there are some building height limitations. Now, stud height and story height are not interchangeable, and you'll see both of these terms crop up throughout the residential code. Story height is limited to 11 foot 7 inches in the current IRC. Stud height can prescriptively go up to 12 feet with restrictions, but story height cannot change, even with that allowance for taller stud heights. So it is possible to prescriptively have stud height of 12 feet per the residential code for localized areas. But if larger areas of wall studs are 12 feet, your bracing would have to be engineered because you're exceeding that story height limitation. When we talk about story height, it's defined as the vertical distance from top to top of 2 successive tiers of beams or finished floor surfaces. And for the topmost story, we're going from the top of floor finish to the top of the ceiling joist. Now, if there are no ceiling joists, we're going from the top of floor finish to the top of the roof rafters. The residential code bracing requirements apply to both balloon framed and platform frame structures. So with balloon framing, the studs get very tall, but they're laterally supported by the floors. And that attachment to the floor is really helping to prevent the tall studs from buckling. For this reason, the stud height is only going to be measured between the floor and ceiling, whether it's balloon framed or platform framed. We're going to move on to irregularities now. Irregularities are one of the biggest differences between wind and seismic design in the residential code. So we're going to spend a good amount of time here. The irregular building section defines buildings that have irregular shapes. These provisions exist to establish shape or geometric limits to structures in high seismic areas. If a building has a shape or condition that exceeds these irregular shape limits, the building or irregular portion of the building needs to get engineered. So let's go through what the residential code considers an irregular building. So these 7 irregular shapes are defined in section R301.2.2.6 of the residential code. When one of the irregular conditions exists, there's either going to be structural requirements or engineering required. Because wading through these can get a bit arduous, we put together a simple decision tree for each irregularity, and we're going to walk through them one by one. I'm going to pause here just to note that the 2021 IRC will include an 8th irregularity restricting use on hillside structures. So it's just a side note, that's coming. This is a blown up view of the decision trees. These are listed in the order they appear in the IRC. So we're going to start on the left with the first irregularity listed in the code and move to the right. The first seismic irregularity relates to our exterior walls. When braced wall panels are not in the same vertical plane, there are both geometric and structural requirements. To still qualify for prescriptive design with the IRC, the depth of setbacks and cantilevers cannot be more than 4 times the nominal floor framing depth. We'll also need to check that any framing that cantilevers past that exterior wall extends at least 2 times that length into the interior of our building. This 2-to-1 backspan ratio and the offset limitation are graphically shown in the lower right-hand corner of your screen. We're going to look at some examples of this, so don't worry if you're having trouble visualizing this in 3D. Once we've established that our offset is less than 4 times the framing depth, and we've got that minimum 2-to-1 backspan ratio, we'll need to meet an additional 5 structural requirements. So number 1, we need to check that our floor joists are a minimum of 2 by 10 in size and space not more than 16 inches on center. Number 2, the floor joists at the ends of any braced wall panels need to be doubled up. Number 3, the rim board needs to be continuous or have an approved splice in it. Number 4, our wall and roof loads need to be uniform. So no extra dormers or chimneys above our offset wall. And number 5, the maximum clear header length in a cantilever or setback needs to be 8 feet or less. So looking at an example, in this photo, you can see the start of the 3rd floor framing with cantilevered eye joists. With these 14-inch eye joists, we're definitely meeting the minimum 2 by 10 floor joist size. And we're just barely meeting the 2-to-1 backspan ratio. But we definitely don't have any double joists. And the offset here is definitely larger than 4 foot 8 inches. If we look at a different example, You can see here we're meeting almost all of the requirements. So our offset is only about a foot. And in the background, you can see the joists extend well back into the building interior. We've got the same 14-inch joist with a continuous rim board at the end of our cantilever. That's this rim board out here. And this cantilever is supporting a uniform load, roof load, with a 5-foot wide window in the wall above. So you can't see the roof or window above in the picture. You're just going to have to trust me on those last two requirements. Irregularity number 2. So floors and roofs that are not laterally supported on all sides are considered irregular. This code section requires that floors and roofs be laterally supported by braced wall lines. There is an exception that permits a laterally unsupported floor or roof to extend up to 6 feet past the nearest braced wall line. So in this graphic, we're looking at a floor extending past the exterior wall for a balcony. You might also encounter this irregularity at a porch area. Roof overhangs are pretty easy to check. We're just looking for whether it's over 6 feet in any direction. Irregularity number 3 is all about braced wall panel placement. So this might be one of the last irregularities you check off. If a braced wall panel is located more than 1 foot over an opening below, there's going to be structural requirements. If that opening is larger than 8 feet, we automatically get kicked into an engineered solution, or we need to adjust our design. But if that opening is 8 feet or less, we need to make sure the entire length of the braced wall panel is not over the opening. It can be in line with the opening. So in other words, the braced wall panel needs to be supported on the studs next to the window opening. The minimum header requirements for that opening below the braced wall panel are listed in the table on the right. Just so you know, these headers also need to meet the gravity provisions, and those are found in table R602.7, parentheses 1. So they'll need to meet both of those requirements. Many designers will stick entirely to the stacked solid wall to place their braced wall panels. This is kind of a luxury that a lot of designs don't accommodate at the front or rear facade of a house. It's really easy to do on the side walls of the house. The picture on the right is an excellent example of a braced wall panel overhanging an opening more than 12 inches. So here the upper floor braced wall panels are overhanging the small windows below by about 2 feet. Now, as long as these headers are at least the equivalent of a double 2x10, this is going to be allowed by the IRC and it won't trigger an irregularity. Braced wall panels over openings are always tempting. If the braced wall panel only overhangs a little, like the picture on the left, then you're in the clear. You cannot put a braced wall panel entirely over an opening though. And if your opening is over 8 feet, you're limited to a 12-inch overhang. The most common place I see this occur is over garage openings. Garage openings are pretty much always going to be over 8 feet, and they often have limited wall area on either side. Irregularity number 4 relates to floor and roof openings. So floors and roofs are acting as diaphragms to transfer that load to the walls. So the code is limiting the size of any disruption in that load path. If these limits are exceeded, the building is considered irregular. There aren't any provisions in the code to permit this irregularity with extra structural requirements. So an opening is limited to half the least floor dimension up to a maximum of 12 feet. And if we don't meet this criteria, an engineer needs to get involved. This is an example of an opening in a floor diaphragm that would require an engineer. This is a volume space between the lower and upper levels. This floor opening is much larger than 12 feet, as well as being over 50% of the building width. So we immediately know we cannot use the residential code for this one. Generally, the rules are going to accommodate stair openings or smaller atriums. Larger spaces open to above, like the photo on the right, typically aren't going to pass. Irregularity number 5 specifically relates to floors. Vertical offsets in floors are considered irregular. There are provisions to permit this, and that's when the floor framing is supported over continuous foundations at the building perimeter, or if the floor framing is lapped and connected per section R502.6.1. Floor offsets aren't really as popular today as they were in the 70s, but occasionally you might see a sunken living room design. The important point here is that we're fully supporting the entire perimeter or lapping the floor framing to create that continuous load path. Number 6, we're almost through. Number 6 is an absolute. So according to the seismic provisions, braced wall lines must be perpendicular to each other. No angled braced wall lines for high seismic. Non-orthogonal or non-perpendicular braced wall panels might not come up as often. Unusual geometry is okay until you try to use it as part of your wall bracing. So on the right, you can see an acute angle at the front wall corner was added as a design feature. The basement window that you see wrapping around the corner tells us they aren't using this as a braced wall panel. On the left, we have a more traditional design with a 2-story silo type space at the entry. Now, as long as we're not using those curved walls for our wall bracing, you can still detail around this. Finally, irregularity number 7. This is all about material weight. So concrete or masonry is heavy, and it's therefore going to have a bigger impact on seismic load. So the code has a number of restrictions around using these heavier materials. Generally, we'll be okay if we isolate these materials to the traditional locations like the foundations and the fireplaces. If you've got a full basement wall like the photo on the right, this level needs to get engineered. If your veneer is thicker than 5 inches, you will also need to engineer this portion of the building. Even for thinner veneers, none of the veneer can exceed 20 feet in any of the seismic design category D regions. That 20-foot height gets extended to 30 feet for gable end walls. So again, if a structure has any of the 7 defined irregular shapes, you're either satisfying structural requirements or you're engineering it. If a building has a shape or condition that exceeds the irregular shape limits that we just went over, the building or a regular portion of the building needs to get engineered. It's easy to talk about high seismic here on the West Coast, where that area comprises basically most of the land area. For the purposes of the residential code, we're defining high seismic as areas where the seismic design category is greater than C, and we're also going to apply this to any townhome located in category C. As a reminder, high seismic doesn't mean we get to ignore wind. So this is the chart that we looked at earlier. The area shaded in blue represents the buildings to which the seismic exemption applies. The area shaded in red represents the buildings that need to meet both wind and seismic requirements of the residential code. So depending on your geometry, one or the other, either wind or seismic might govern. Because seismic load is based on mass, the residential code restricts the dead load or weight of the building. The residential code limits building weights, as shown on this slide, for roof, floor, and wall assemblies for buildings located in high seismic regions. These weight limitations aren't going to apply to low seismic regions or regions with that seismic exemption. So this is a common assembly we see here in the Western United States. You can see that the residential code is going to cover some common types of roofing, but as soon as we switch to Spanish tile or slate, you'll likely get bumped back into the regular building code, or you'll have to increase your wall bracing. But be careful with the increased wall bracing. You can see in the lower right of the screen that the increased weight carries a pretty hefty penalty, increasing your bracing requirement by 20%. So this is a really big deal. We put together this list really to give you a starting point right around the weight limit. Obviously, when you evaluate the loads for your particular project, you're going to want to independently verify the weights of the specific materials that you're using. Floor loads similarly are limited to lighter weight floor coverings. I'm going to point out here that the limit is for the overall average weight of the floor. So you might have some small areas of bathroom tile, but the average over the entire floor should be limited to 10 pounds per square foot or 10 PSF. Exterior wall assemblies can vary a lot depending on the climate region and the house style. If we look at all the things in this particular wall assembly, you can see we've got gypboard at the interior, our wall studs, a layer of OSB or oriented strand board, the batt insulation, a wood lap siding, and an extra pound for miscellaneous items like blocking or electrical boxes. We've also included a couple other common dead loads you might be seeing in your area just as a general reference. Again, you should verify the materials you actually intend to use on any project. Interior wall assemblies usually have fewer layers and they tend to be a bit lighter. So here you can see we're right around 7 pounds per square foot, and that's less than half the weight of the exterior wall assembly on the previous slide. A good portion of California and Hawaii, as well as a few select other areas of the United States, fall into seismic design category E. There are select instances where the code allows us to reclassify seismic design category E buildings into seismic design category D2. Some areas labeled as seismic design category E in the residential code may fall under seismic design category D in the IBC, so those can get reclassified as seismic design category D2. If that's not true, we can meet some tighter restrictions and still reclassify our building as seismic design category D2. So I've listed those restrictions out here, and I'd like to note that the restriction against floors cantilevering past the exterior wall means that we're never going to have that first irregularity of the cantilever and setback irregularity. No exceptions. You're not allowed to do that if you are reclassifying your building. Once you've established that the project meets the basic residential code requirements, now it's time to look at the lateral system. So we're going to start by looking at the various wall bracing types. If you watched the earlier modules, this is going to feel a bit repetitive, so hopefully you can bear with us. So the bracing methods allowed in the residential code are divided into two categories: intermittent and continuous. There are 12 different intermittent bracing methods. These are the first 6. Since we're talking about high seismic today, we're skipping lead-in bracing. Lead-in bracing is not allowed except in the very top floor of townhouses in seismic design category C. Likewise, we're going to skip garage portal frames, which are also limited to townhomes in seismic design category C. So starting with DWB, or diagonal wood board method. You might see this diagonal board style sheathing in some older homes, but it's a little less popular these days. This is a very strong system, but it's going to add more thickness to the wall assembly and requires a lot more fasteners. I'd also like to note here, if you're used to designing specifically just for wind, the wind tables in the IRC group DWB with the WSP, or wood structural panel method. However, the seismic performance is not similar. So when calculating your seismic wall length, DWB is going to require more length than a WSP, or wood structural panel method. Like most intermittent methods, these panels require a minimum 48-inch width for walls up to 10 feet tall. This is very typical of intermittent methods. So WSP, or wood structural panel method, uses either plywood or OSB conforming to PS1 or PS2. These panels are required to have 6-inch on-center edge nailing and 12-inch on-center nailing in the field of the panel. Based on wind speed, exposure category, and stud spacing, the minimum thickness category may be increased to 7/16 with a minimum 8-penny nailing. This is really only going to apply in special wind regions or exposure D, that's wind exposure D locations, where the studs are spaced at 24 inches on center. Otherwise, the minimum thickness category for your panels is 3/8. Method SFB, or structural fiberboard sheathing, requires a minimum thickness of a 1/2 inch and to be installed on studs spaced not greater than 16 inches on center. Note the minimum fastener spacing is 3-inch on center at the edges and 6 inches on center at the intermediate supports. That nailing was increased to match the lateral or shear capacity of other panel type products like the WSP method or the diagonal wood board method. So GB, or gypsum board method, is very popular for interior wall lines. The gypsum board needs to be at least a 1/2 inch thick, and the maximum stud spacing is 24 inches on center. When the gypsum board is installed on only one side of the wall, only half of the actual wall length counts towards your total. The minimum braced wall panel length is 48 inches for any wall up to 10 feet. So if you have a 4-foot panel length and the gypsum board is only on one side, that's only going to count as 2 feet towards your braced wall length. Also note, floating corners are not allowed. So floating corners occur when the edge of the gypsum board ends between framing members and is therefore kind of floating out in space. PBS, or particle board sheathing, will have a similar thickness, but with narrower 16-inch on center stud spacing. Just like with the SFB method, the nailing for the PBS method increases to 3 inches on center at the edge and 6 inches on center over intermediate supports. And this is to match that lateral or shear capacity of the other panel methods. PCP, or Portland cement plaster, is also going to require 16-inch on center stud spacing, but the 6-inch on center nailing requirement is going to apply to all framing members, whether it's at the edge of the panel or at the interior. HPS, or hardboard panel siding method, is going to have a similar thickness to the WSP method, but the fastener spacing here is 4 inches on center at the edge and 8 inches on center over intermediate supports, with studs spaced at a maximum of 16 inches on center. So just like most of the intermittent methods, HPS requires a minimum wall panel length of 48 inches. Now, unlike most intermittent methods, ABW only requires 32 inches of wall length in high seismic areas. Construction of ABW, or alternate braced wall panel method, requires 3/8 minimum thickness category wood structural panels. So that's either plywood or OSB. And the capacity of the hold downs are given in the IRC table. That's table R602.10.6.1. The hold down capacity is a function of the wall height, so the taller walls are going to require a larger hold down capacity. If the ABW is supporting a story above, not only will the hold down capacity increase, but the wall sheathing needs to get nailed at 4 inches on center max around the edges. I think the cool thing about these panels is that they count as a full 4 feet. So even though they're only 32 inches wide, they're going to count as a full 4 feet of panel length towards your required panel length along a braced wall line. Because this method requires hold downs, we're only ever going to place these at the ground floor with the foundation below. PFH, or portal frame with hold downs, will similarly only be placed at the ground floor. Other than ABW, this is the only other intermittent method that allows a panel length under 48 inches. These panels need to be constructed from plywood or OSB. The required hold down capacity is 3,500 pounds for both the 16-inch and 24-inch wall lengths. This frame was included in the residential code based on testing and consequently has very specific detailing requirements like this 10-foot maximum height. Notice the extended header and the grid nailing at 3 inches on center. This is a moment resisting connection, and that allows the brace wall panel to be narrower than other intermittent wall bracing methods. 3-inch on center nailing is also required at the double studs on each side and at the bottom plates. If your wall's a little bit taller, don't worry, the code does allow for a short pony wall above the header. Again, we're seeing that 12-foot maximum wall height, but the height of the frame measured from the top of the header is going to be limited to 10 feet. When we place that pony wall above the header, the wall gets a vertical strap shown in the upper right of the diagram. So it's this strap right here. This strap goes on the opposite side of the wall from the sheathing. If you'd like to learn more about portal frame detailing, because there's a lot of details here, there is a free 30-minute webinar on APA's website, so you can go check that out. Moving on to continuous sheathing methods. So there are 4 total continuous sheathing methods. Because we're in high seismic, we're going to knock this down to 3. And we're going to add an asterisk to CSG. So in high seismic, CSG can only be used where supporting a single gable end wall with a roof covering weight less than 3 pounds per square foot. Now, if you recall our earlier example of roof weights, the 3 PSF was about the weight for a 3-tab shingle with felt. For all methods, the wall lines must be fully sheathed, and that's going to include that gable end. All 3 of these remaining continuous sheathing methods use either plywood or OSB. The minimum width of a panel will directly depend on the wall height. So for both CSWSP or CSG, the tables are limiting the height to width aspect ratio of each panel to 4:1. Both of these methods have similar detailing, unlike the CSPF method, which is going to mimic the PFH detailing we just went over. So that takes us through all of the bracing types. I'm gonna hand the presentation over to Larry to talk about how to lay out these elements in plan.
Yeah, thanks, Alita, and hello, everyone. Now let's look at how we incorporate wall bracing into our building plans. Braced wall lines are not to be confused with braced wall panels. Braced wall panels can lie directly on or immediately adjacent to a braced wall line. The residential code defines a braced wall line as a straight line through a building plan representing the location of lateral resistance provided by the wall bracing. When there is a single wall, the braced wall line is placed on the wall. When there are multiple segments of the wall, the braced wall line may be placed between or adjacent to the segments of wall lines. The spacing permitted between parallel braced wall lines depends on whether wind or seismic requirements are considered. For high seismic regions, SDC C through D2, the seismic design limits the braced wall line spacing to a maximum of 25 feet. However, there are a couple of exceptions which can allow spacing more than 25 feet. You can see the two exceptions listed in the bottom left of the slide. These two adjustments to the required braced wall line length for seismic may allow spacing up to 35 feet. Braced wall lines need to follow these 7 guidelines. The first 3 items in the list are pretty basic. We're mainly setting up grid lines in those. But the 4th and 5th items in the list are important. To get a better understanding of what they mean, we're going to look at a few examples in the next slides, which may be refreshers from our previous wall bracing webinars. We felt it was important to emphasize a few often used concepts before we work our way into more specific high seismic topics. So looking at this plan, do we need to add a braced wall line at the 6-foot offset wall because the distance between wall lines is greater than 4 feet? The answer is braced wall lines don't have to fall on physical walls and offsets of 4 feet are permitted. Since the wall lines are less than 8 feet apart, a single braced wall line may be placed between the 2 walls. We call this an effective or imaginary braced wall line. Does this wall line meet code? The answer is yes. The wall line offset is not more than 4 feet from the imaginary braced wall line. In this example, because of the 4-foot dimension between walls, one could have also placed the braced wall line along either wall segment. Does this braced wall line meet code? Again, the answer is yes. The wall line offset is not more than 4 feet, and the placement of the braced wall line as shown includes all exterior walls. So how many braced wall lines are in this example? Remember that a braced wall line can have offsets up to 4 feet and a total out-to-out offset of 8 feet. We could have defined a braced wall line that passes through wall segment A, or we could have defined a braced wall line passing through wall segment C. But if we draw the braced wall line through wall segment B, segments A, B, and C can be considered as one braced wall line. A provision for angled braced wall lines was added in the 2009 IRC. The angled section is considered part of the braced wall line to which it makes the smallest angle change. In this example, due to the angled wall portion is part of braced wall line 1 rather than braced wall line A. If the angled wall shown in this example was at 45-degree angle, it must be considered as an extension to one of the 2 walls. It cannot be considered an extension of both walls. If the wall section is longer than 8 feet, per high seismic irregularities, you might consider having the wall engineered or excluding it from your prescriptive wall bracing calculations. In high seismic, there has to be a braced wall panel at the beginning and end of each braced wall line. This can only be avoided if using wood structural panels in your bracing method, and even then, it will often require hold downs. If you're using any of the continuously sheathed bracing methods, the wood structural braced wall panels can begin up to 10 feet away from the end of the braced wall line, provided there are either hold downs or 24-inch wide return panels. This is true even when the required bracing length for wind is greater than the required bracing length for seismic. The picture on the left in the slide shows the use of a hold down, and the picture on the right shows a 24-inch wide return panel. Note, you might infer from this code section that a 24-inch panel and an 1,800-pound hold down are structurally equivalent. Once the braced wall lines are laid out and possible braced wall panels are identified, we need to check that we're meeting the code required total length of braced wall panels. To calculate the minimum total required length of braced wall panels, we're going to look at table R602.10.3, parentheses 3. Looking at the columns and going from left to right, this table is organized first by the seismic design category, then the story location of the bracing, then the braced wall line length from which you determine the total length of braced wall panels required based upon your braced wall method. As a reminder, for seismic, we look at braced wall line length in the table instead of braced wall line spacing we used for the wind table. So in the seismic table here, as you move down the table within a story, you can see the amount of required braced wall panels increases based upon the braced wall length. Generally speaking, just looking at the columns of various braced wall methods in the table, the required braced wall length decreases as we move from left to right. The last two columns of the table represent the bracing methods used for structural wood panel. You might notice in the upper left corner of the table, there's a list of assumptions used for the basis of the table values. After you establish your required total length of braced wall panels from this table, you'll apply adjustments to that length per the seismic adjustment table. These adjustments account for deviations from the base assumptions. Let's look at that adjustment table now. When the design deviates from the base assumptions we saw on the last slide, we noted that you need to adjust the total required length of bracing. We've talked about most of these limitations already, but I'd like to specifically point out the last two items. Number 9 can apply to about half of the bracing methods used today. Naturally, this adjustment will not apply when using the gypsum board method. It also won't apply for any of the portal frame methods. Number 10 is going to apply only when using WSP or CSWSP as your brace panel method. After applying the adjustment factors and calculating the total required length of braced wall panels for each braced wall line, you'll need to look at your wall elevation to determine how much of your total wall length can qualify as braced wall panels. The goal is to physically provide more braced wall panels than that required by code. Remember, braced wall panels need to be full height. Unfortunately, this isn't as simple as adding up the total lengths of full height wall sections. If a panel doesn't meet those minimum widths we discussed earlier, it doesn't count. We'll elaborate on the rules of mixing intermittent and continuously sheathed braced wall methods in a bit. But for an example on calculating wall bracing contributing length, let's look at this house elevation and start off by discussing intermittent methods. Most of your intermittent methods will only count the blue highlighted wall areas. This is because most intermittent braced wall panel types require a minimum width of 48 inches to be considered a braced wall panel. The exceptions being alternate braced wall panels and portal frames, which can also be used with continuously sheathed methods. While seismic design categories A through C will allow you to take some partial credit for methods less than 48 inches, partial credit is not available to use in higher seismic design categories. If we incorporate an ABW along the right side of this wall line, we can use some additional panel segments that are over 32 inches wide. Remember, each ABW will count as 4 feet. So this will add a full 12 feet to our contributing braced wall length. Alternately, if we use continuously sheathing on the wall and calculate our contributing CSWSP segments from the partial credit table using 4-foot window height, we find the minimum width allowed is 24 inches. Because all of the wall segments shown in this slide are greater than 24 inches, we can use the total of all the full height CSWSP wall lengths, which in this example totals 42 feet, 5 inches. Note for clarity in the elevation, we've highlighted the contributing CSWSP panels, even though the wall area above and below our windows will be fully sheathed. So you can see there can be definite advantages to mixing wall bracing types. The code does allow some types of mixing even in high seismic, but there are restrictions. The next slides will review those restrictions. Code permits a variation in bracing methods between stories. So no matter what region you're in, you can use an intermittent method on one story and a continuous method on another story. The code also permits a variation of bracing methods between braced wall lines in the same story. In the high seismic design categories, you cannot mix continuous and intermittent methods within a single story, but you can mix intermittent methods within a story. For example, you can use intermittent WSP on the exterior braced wall line and GP on an interior braced wall line within the same story. We just clarified mixing within a story. Now let's focus on the individual braced wall lines. Mixing intermittent methods within a single wall line is not allowed in high seismic areas D0 and greater. The code will allow you to mix continuous sheathing methods that use wood structural panels. So within a single braced wall line, you cannot mix intermittent methods, but you can mix continuous wood sheathed methods. If you're using a continuously sheathed method and some of your wall piers are just a bit too narrow, the code allows you to mix in an alternate braced wall or a portal frame. In general, intermittent methods require more bracing length than continuously sheathed methods. So when mixing in the ABW or portal frame methods with your CSWSP methods, your required bracing length will go up because now you're going to need to meet the same length requirement as if you used all intermittent methods. This is a cheat sheet table of everything we just discussed. Notice the last line in the table. Mixing an interior gypsum board with a continuous exterior sheathing method is really common in a large portion of the US, but it is not allowed in high seismic design categories. For example, if you're building an L-shaped building in Indiana, you might see a wall line switch from type CSWSP at the exterior to type GB at the interior. If you build the same house in a high seismic region, you'll see CSWSP along the entire braced wall line. Now that we've covered the big picture items, let's drill down and discuss special high seismic detailing requirements. In the next few slides, we'll look at some special connection details. Let's look at this roof connection detail, where the distance from the top of the braced wall panel to the top of the rafters or roof trusses is 15¼ inches or less. Blocking between rafters or roof trusses shall be provided above the braced wall panel per figure R602.10.8.2 Where the distance from the top of the braced wall panel to the top of the rafters or roof trusses exceed 15¼ inches, refer to the figures 602.10.8.2 parentheses 2 and 3. While the residential code requires all joist ends to be supported laterally, This support is extended to all intermediate supports when building in high seismic design categories. So if your joists are continuous over a bearing wall, there needs to be blocking between the joists in high seismic. Adhesive attachment of bracing panels is not permitted. This applies to all residences in SDC C through D2. High seismic also has some additional foundation requirements. A foundation is the last major component of a structure's lateral load path. The foundation needs to resist both sliding and overturning. Section R403.1 states that all exterior walls shall be supported on continuous, solid, or fully grouted masonry or concrete footings or other approved structural systems which are of sufficient design to transmit the resulting loads to the soil. For SDC D0 and D1, all exterior walls require a continuous footing. Interior continuous footings are required where one of the plan dimensions exceeds 50 feet. For SDC D0 and D1 2 stories, there is a conditional exception which we'll go over shortly. The requirements for SDC D2 get more stringent as soon as we add a second story. If we've got 2 stories, all the interior braced wall panels need to be supported on a continuous footing unless we meet the exception requirements. So in the last couple slides, we've mentioned an exception. This slide lists the R403.1.2 exception. Admittedly, the R403.1.2 section and the exception can be difficult to understand. This 2-story exception, which applies to SDC D0 through D2, gives you the opportunity to not have continuous foundations under some of the interior footings. The SDC D0 through D2 2-story exception can allow interior wall lines with braced wall panels to be supported according to the 3 criteria listed in the slide if footings below interior braced wall panels are spaced at a maximum of 50 feet. Here's 2 examples of applying the exception to a 2-story structure. Assuming any Cripple walls are less than 4 feet and interior footings are not more than 50 feet apart, we can have first floor panels supported on double floor joists, continuous blocking, or floor beams. The green highlights in the slide are where we use floor beams, and the yellow highlights are where we use double joists to support braced wall panels above. It is important to note that we have left the interior footings at braced wall line C to keep the spacing of the continuous interior footings under the 50-foot exception requirement. So this raises a question that we often get. Do you think the exception should also be applied to 1-story buildings? It's APA's interpretation that this exception should also be allowed for 1-story building. When you think about seismic loads being a function of mass, and a 1-story structure has less mass. But ultimately, that interpretation is up to the local building official's decision because the code clearly states just 2-story. Let's continue discussing more foundation requirements by using illustrations. Per R403.1.2, in SDC D0, D1, and D2 1-story buildings, all exterior walls shall be supported by continuous footings. The interior braced wall panels do not require continuous footings unless one or more plan dimension is greater than 50 feet. If one plan dimension is greater than 50 feet, continuous footings are required below all interior wall braced panels. In this example, assume gray walls are interior braced wall panels. Exterior braced wall lines 1, 3, A, and E require continuous footings. Remember that exterior walls, braced or not, shall be supported by continuous foundations. Braced wall lines B, C, and D need continuous footings below the interior braced wall panels because one plan dimension is greater than 50 feet. In our example, we have 82 feet in the horizontal direction. For the other direction, interior braced wall line 2 would also require a continuous foundation because, again, one or more plan dimension is greater than 50 feet. In two-story buildings located in SDC D0 and D1, all exterior walls shall be supported on continuous foundations. No continuous footings are required at interior braced wall panels if both the plan dimensions are less than or equal to 50 feet. If one or more plan dimension is greater than 50 feet, continuous footings are required below all interior braced wall panels unless the exception is used. In two-story buildings located in SDC D2, again, all interior and exterior braced wall panels shall be supported on continuous foundations unless the exception is used. Here's a chart from the IRC commentary which summarizes our previous foundation discussions. The oval in the one-story row highlights the section where we'd like to see the exception be applicable. Again, it's APA's interpretation that the exception specifically listed for just two-story structures could be used for one-story structures as well. And again, I must caution you to check with your local building official. The foundation size is going to be based on your soil properties. If you're working on a large subdivision site, it might be worth hiring a geotechnical engineer to obtain your specific soil capacity. If the project is smaller, hiring a geotechnical engineer might not be feasible. In that case, you can reference this table for some basic soil capacities. If you're still not sure what you've got, you can generally design using the lowest value of 1,500 pounds per square foot. But look at footnote B of the table. The best advice is to check with your local jurisdiction. Remember, the value you decide upon is going to be the basis of all your foundation design. For your continuous footings, you get a table which we will show you in the next slide. In this table, you're going to cross-reference the soil capacity with your building size. This table is all about gravity loads, which is why we're differentiating between a one-story and a two-story house. You'll notice a lot of 12-inch by 6 inches in the table. No matter how good your soil is or how small your structure, 6 inches thick is the thinnest footing you can use. You could wind up with less than 12 inches wide though. The table was developed assuming a 32-foot wide house. Footnote B allows us to adjust for your project by adding or subtracting to the footing width. If you've got veneer or masonry, you're going to look at similar but separate tables. It's important to note that the 6-inch minimum thickness does not mean you only need to dig a 6-inch pit for your foundation. If you're used to seeing slab-on-grade construction poured monolithically, also known as the same time, with a continuous footing, this difference between depth and thickness might not be apparent. If you're building in colder areas of the country, you probably see details more like this. Here you can clearly see the width and thickness specified in the table is provided well below grade. At a minimum, the bottom of any exterior footing must be 12 inches below grade. For SDC D0 and higher, the 12-inch minimum also applies to interior footings under braced wall panels and bearing walls. If your project is subject to frost, you need to go look at section R403.3 for frost-protected shallow foundations. Table R403.3 parentheses 1 will give you a minimum depth based on your air freezing index. This section lists the air freezing index number by state and county. See figure R403.1.3, which is titled Reinforced Concrete Footings and Masonry and Concrete Stem Walls in SDC D0, D1, and D2. This slide summarizes some of the more typical foundation provisions. Let's look at some of these details in the following slides. Here's two pictures showing the requirements of section R403.1.3.1. The details shown are the same for both interior and exterior stem wall footings. If a construction joint is used in high seismic categories, vertical reinforcement is required every 4 feet. Here's two pictures showing the requirements of section R403.1.3.3 for slabs on grade with turn down footings. The details shown on both drawings are required for both interior and exterior footings. If a construction joint is used in high seismic zones, like the joint shown in the figure on the left, a minimum number 3 vertical reinforcement is required every 4 feet for either interior or exterior turn down slabs. There are some additional requirements for foundation walls in section R404.1.4 for SDC D0 through D2. Here are some of the more typical special requirements. Masonry has a special requirement for SDC D0 through D2 in section R401.4.1. One example for masonry is that masonry walls cannot exceed 8 feet. Here we continue looking at additional requirements. Let's look at the second row in the table, which refers to section R602.10.9.4, which states concrete or masonry stem walls less than 48 inches require specific reinforcement. This shows the required reinforcement for walls supporting bracing elements. The figure shows masonry, but also applies to cast-in-place concrete, with the exception that ABW and BFH methods are not to be used on masonry stem walls. Getting our lateral loads into the foundation will also require a bit more anchorage attention. Plate washers shall be provided between the foundation sill plate and the nut, except where approved anchor straps are used. The hole in the plate washer is permitted to be diagonally slotted with a width up to 3/16 of an inch larger than the bolt diameter and a slot length not to exceed 1 3/4 inches, provided that a standard cut washer is placed between the plate washer and the nut. Please note, washers are required for the entire braced wall line. The code also has provisions for spacing of sill bolts and requires a minimum 1/2 inch diameter bolt with 7 inches of embedment. For additional information on anchorage requirements, please refer to this slide in your handout. Note that other than the red font, the first row is a summary of your anchorage requirements regardless of seismic design category. Cripple walls and crawl spaces tend to be more common in colder regions. There are a lot of requirements specific to cripple walls in this code. This section will highlight many of those requirements. It's important to focus on the definition of a cripple wall, which is defined as the framed wall from the foundation to underside of the first floor framing. Dependent upon region, cripple walls may also be called knee walls, pony walls, or short foundation walls. Cripple walls are often used with step foundations on slope building sites to maintain a level first floor. However a cripple wall is used, it has the same limitations as any other stud wall in that it has no lateral load capacity without the use of bracing panels. Therefore, cripple walls must be constructed following the provisions of section R602.9. Here are some of the main concepts about cripple walls. It is important to note, especially when we think about crawl spaces, that braced cripple walls must be supported on continuous foundations. The code allows the designer to consider two methods for determining the required braced panel length of the cripple wall. One way is per the provisions of section R602.10.10 for cripple wall bracing, and the other is per R602.10.10.3, redesignation of cripple walls. Before we look at redesignation, let's start by considering the level below the first story as the cripple wall story. The cripple wall story should be braced with the same material and length as used in the first story braced wall panels, and you need to apply adjustments where applicable. Use a 1.15 factor as part of calculating the required cripple wall bracing length, except for SDC D2, where you refer to tables R602.10.3 parentheses 3 and R602.1.3 parentheses 4. Use a factor of 1.5 for seismic or 1.4 for wind if gypsum is not used on the inside face of the cripple wall. Apply an additional factor of 1.5 if the first floor braced wall lines are allowed not to be supported on continuous footings. And finally, other than SDC D2, you may use an optional factor of 0.7 if the fastener spacing at the panel edges and any blocking are 4 inches on center. Let's look at the cripple walls and the two methods of design we previously mentioned. Per R602.10.10, cripple walls shall be braced with the length and method of bracing used for the wall above in accordance with seismic and wind tables and their applicable adjustment factors. The length determined shall also be multiplied by the factor of 1.15. The other way of designing is redesignating the cripple wall as the first story per R602.10.10.3. Redesignation is optional if the entire cripple wall is less than 48 inches, but redesignation is mandatory if any cripple wall segment exceeds 48 inches in height. If you use redesignation, the spacing between braced wall panels is limited to 20 feet. If the cripple wall is redesignated, the first full height story becomes the second story. You can see how the house on the left was redesignated to the figure on the right. Here's an example for a two-story structure above a cripple wall. Note in the right figure, when the cripple wall is redesignated as a story, the story count changes from the figure on the left. When you're in SDC D2, the amount of cripple wall bracing is specified directly in the seismic table, or you can redesignate a one-story structure as a two-story. Cripple walls in SDC D2 must use WSP or CSWSP methods as noted in table R602.10.3 parentheses 3. Note that we haven't addressed BVWSP because cripple walls are not allowed when using BVWSP methods. A two-story structure cannot be redesignated as a three-story in SDC D2 without getting an engineer to design the first story. When calculating cripple wall bracing where braced wall lines and interior wall lines are not supported on a continuous foundation below, the adjacent parallel cripple walls, braced lines A and C in the plan, shall be braced with method WSP or method CSWSP. The length of the bracing required for the adjacent cripple walls on braced wall lines A and C shall be multiplied by a factor of 1.5. And note this 1.5 factor is in addition to the 1.15 factor discussed earlier. If the required cripple wall bracing length is getting too long, say for braced wall lines at A and C, you could apply a factor of 0.7 to the required wall bracing length if you use 4-inch on center panel edge nailing. Now let's consider cripple wall placement over stepped foundations. Looking at the left side of the diagram, if the footing length A is 8 feet or more in a 25-foot wall line, the wall line is considered braced. Note that the metal tie is required for the wall to be considered braced. In high seismic areas, if the footing length of a cripple wall is 8 feet or more, the braced wall line can be considered braced if all the provisions of R602.11.2 are met. So the question comes up considering this provision in designing for wind or lower STZ zones. If this same type of cripple wall construction is used in a low seismic area, could the braced wall line be considered braced? It would seem to APA that a provision that exists for a high seismic category would also be applicable for a low seismic category. Here's the splice detail for the double top plate of a cripple wall when the bracing requirement is met by direct attachment to the foundation. Note the 4-foot minimum dimension in the detail. For step foundations in SDC D0 through SDC D2, refer to section R602.11.2, which provides requirements for the construction of the braced wall line. In this example, the bottom of the footing is stepped rather than the top of the footing. This is permitted. Just like in our typical story walls, we don't get to stack 2 walls and call it good. This stacked configuration creates a hinge where the sill plate from the upper wall meets the top plate of the bottom wall. Let's look at these pictures and think about what if the walls shown were used as cripple wall bracing in a crawl space. For starters, remember that cripple walls shall be braced with the lengthened method of bracing used for the walls above. This is a main requirement for the prescriptive code compliance. Secondly, the picture brings up the question, what if method GP was used for the braced wall panels above the cripple wall shown in the crawl space? I would think that rather than using gypboard in the crawl space, method WSP might be an acceptable solution to your local building official. Another thought is, what about the requirement for continuous interior foundations in high seismic design categories? Note the picture on the left doesn't have continuous footings. Therefore, the cripple walls as shown may not meet prescriptive code wall bracing. In contrast, the pictures on the right side of the slide are examples of continuous footings in a crawl space. One thing to consider about designing wall bracing for cripple walls in crawl spaces is the crawl space wall bracing could be engineered, while any upper floors are designed using code prescriptive wall bracing methods. This might be considered kind of a hybrid design approach. The wall top plates are used prescriptively to carry the lateral load to the braced wall panels. The residential code therefore sets some minimums on how you splice these top plates. A minimum of 8 16D nails are required on each side of the splice. We've only included the double top plate splice detail. If you're using a single top plate, you'll need to refer to table R602.3.2. In essence, the double top plates often act like a collector. So what is a collector? A collector is a link in your lateral load path. So far, we've mostly talked about braced wall lines and braced wall panels. Collectors are a structural element that gathers or collects lateral load along its length and delivers it to a braced wall panel. For conventional wood framing, the wall top plates are usually acting as the collector. Collectors will resist those lateral loads in both tension and compression, depending upon the direction the wind is blowing or the earth is shaking. This should help explain why top plate splices are so important. If we use our top plates as the collector, those 2x pieces are getting pushed and pulled. If we don't get enough nails in that splice, the pieces can separate, cutting off our load path before it ever gets to our braced wall panels. Prescriptive requirements limit the spacing of braced wall panel as well as their distance from the end of the wall. When you exceed these limits, special collector design is required. APA put together a top plate splice table to help you with varying distances from the wall end. You can find this table in our publication form TT102. APA has a wall bracing calculator available on our website. The calculator is updated for every code cycle beginning with 2009 and is currently updated through the 2018 IRC. There is a downloadable quick start guide and a short step-by-step video available at our APA wall bracing webpage. Here's a couple of great wall bracing resources that you may be interested in. On the left is a book for purchase titled A Guide to the 2018 IRC Wood Wall Bracing Provisions, which was co-authored by the ICC and APA. Another resource on the right is the free APA publication, Introduction to Wall Bracing. Both of these publications can be accessed through our APA's wall bracing webpage. So what's coming next? The 2021 IRC changes include some general updates, but most notably, there's going to be an 8th irregularity added that'll limit the average slope to 1 in 5 and a 7-foot maximum cripple wall height. An exception was added, increasing the allowable story height to 13 foot 7 inches for buildings with stud heights up to 12 feet. The amount of offset braced wall panel length on a single side of the associated braced wall line is going to be limited to 2/3 of the total required length. This is a big deal for your effective or imaginary braced wall line placement. PFH, ABW, or BVWSP with hold downs are now allowed up to 10 feet from the braced wall line end. Veneer will be limited to the first story for townhomes in SDC D0 through D2. And for detached homes, BVWSP is not required where the veneer only occurs at the first story. Where veneer extends above the first story, there are some additional forthcoming exceptions and options. The big change, if your project has a crawl space, is the new requirement for preservative treatment of any columns within 8 inches of the ground. So let's look back and summarize our learning objectives. So Alita went through the differences between IRC and IBC design and talked about loads and irregularities. She then showed us a great irregularity flow chart and went through examples for each of the 7 different irregularities. We both talked about different wall bracing types and spotlighted the specific peculiarities of high seismic design. And after showing you several specific rules, I shared with you a very useful mixing rule table for your future reference. It is our intent that this presentation and course handout should provide an excellent resource for working through prescriptive high seismic wall bracing. So at this time, I'll turn the controls back to our moderator, Karen Beebe, who will finish up today's presentation.
Thank you, Larry and Alita. Before we get into our Q&A, I just wanted to remind everyone that your feedback is very important to us. Here we go, see our QR code will magically appear once again so that we can all take a moment and fill out that survey, give us feedback on what you liked, what you'd like to see different on our next webinar. So let's give Larry a break and we'll jump into some questions for Alita first. I appreciate all of the questions that came in during the session. We answered as many as we could. Let's start with one about imaginary braced wall lines, Alita. So specifically, can you use an imaginary braced wall line offset from the physical wall line to reduce the spacing between your braced wall lines?
I think you're talking about when sometimes a designer will stack all the braced wall panels on a single side of a braced wall line, and that's just to meet the, so they're not exceeding that maximum braced wall line spacing. That's not really the intent of the 4-foot offset. I think as the code is written right now, it's up to the interpretation of your building official. Larry did mention in the 2021 IRC that it's going to be clarified a little bit, and it should address this by limiting the percentage of the braced wall panel length that's on any one side of your braced wall line. So you won't be able to stack them all on one side of your braced wall line with the 2021 IRC.
Thanks, Alita. And that also reminds me of another question I got very early on was, what code is this based on? So this is the 2018 IRC for this particular set of slides, and that last slide about what's coming next is 2021. Another question for Alita. Why isn't ABW, the alternate braced wall method, used more in high seismic bracing?
The alternate braced wall method is kind of interesting. So it's an intermittent bracing method, not a continuous bracing method. Because we're in high seismic, we're not allowed to mix intermittent braced wall methods along a single braced wall line. We can mix it with continuously sheathed methods, but as soon as we mix that intermittent method with the continuously sheathed method, we end up needing a longer overall length. So substituting that in, just in practice, it's not very effective for meeting that length requirement. It's more effective to use a continuously sheathed method and maybe substitute in a continuously sheathed portal frame or something if you need to take advantage of that narrower pier width.
Yeah, and the ABW only goes down to about 32 inches, right?
Right, and that portal frame can get you down to 24 inches or less, depending on your wall geometry.
Thanks. How about another bracing method question? When do you use BV-WSP, the brick veneer with wood structural panel wall bracing in high seismic?
Yeah, I got a similar question not that long ago. I know I grew up in a house that had like a 3-foot high brick veneer around the outside, and as long as that veneer isn't going above that first story level, if it's staying on that ground story, you don't need to use BV-WSP. But as soon as you go above that that second story or that first story height, you're going to need to use BV-WSP.
Thanks, Alita. And Larry, we need to pull you back in here. So a couple of braced wall line and foundation questions. Do I need a continuous foundation under the entire braced wall line or just the braced wall panel?
When I think about answering that, I think about answering it looking at both exterior and interior footings. So it's pretty easier when I think about exterior footings because the high seismic design code says that you have to have continuous support or continuous foundations under all exterior walls, whether they're braced or not. Where the answer gets a little more complicated is when you consider interior footings. Interior braced wall panels do not require continuous footings unless one or more dimension is greater than 50 feet or you're working with SDC D2. Keep in mind that you still can use the exception to reduce the number of continuous footings on the interiors when they are required, as long as you stay within the provisions of that exception. So to wrap it up, technically, where the interior continuous foundation is required, it is only required where the actual braced wall panel is and not necessarily the entire braced wall line.
Thanks, Larry. That was a very comprehensive answer and a tricky question. So hopefully that was what the asker was looking for. If not, you can shoot us an additional email. We'll follow up further. Maybe a little easier question here. Won't adding interior braced wall lines for seismic cause an increase in the wall bracing needed for wind?
I think that question is probably generated when you consider the wind adjustment tables, and with the more braced wall lines that you have to apply a factor. So I think if you go from 2 to 3 braced wall lines in wind, it's a 1.3 factor that you would use. So when designing for wind, the IRC allows you to ignore the interior seismic braced wall lines and calculate that structure as if it was just for wind only. You then would have to calculate the seismic bracing based upon all of the seismic braced wall lines and use the most conservative result from both of those analysis.
Great, thank you, Larry. That is a common question that comes up in my experience as well. Question says, section R602.10.1.1 says the end of a braced wall line is at the intersection with a perpendicular braced wall line. What if there's no physical wall at this intersection?
That's a common one when you think about imaginary brace lines, which may not occur on a physical wall, and the intersection may not occur on a wall. So to satisfy the end condition for wood structural wood panel methods, the 2-foot return walls only need to be provided at the very ends of the closest physical wall line.
Thank you. And looking at our clock, we're running out of time here, but I'm going to throw one more at you, Larry. If my brace wall line is intersected by 4 perpendicular brace wall lines, do I need brace wall panels or return walls at every intersection?
The short answer is not necessarily. It's true that every braced wall needs to intersect 2 perpendicular braced wall lines in order for you to calculate its length. The requirement for braced wall panels at the start and end of a braced wall line are not necessarily going to occur at every one of those intersections. The requirement for the placement of the braced wall panels will depend upon what you are using as your total braced wall length.
Yeah, I think a lot of these questions would benefit from a drawing if we could, go to the chalkboard and show what we're talking about. And so I would recommend, as a designer, if you can put as much of that on your plan view to make it as clear as possible for the plan checker and the builder, then that would go a long way to making it easier for all parties involved. So at this point, I think we're going to wrap up our Q&A. I want to thank Alita and Larry again. If we did not address your question, please, we're going to pass those questions along to our field services team and get back to you as soon as we can. Before we conclude, I would like to touch on a few last minute things. Don't forget to download your AIA or ICC certificate of completion. Make sure that you're signed up to receive our APA update newsletter so that you'll be notified of our future webinars and standards. To receive it, all you need to do from our homepage is to click on Sign In the upper right-hand corner of the page. In the drop-down menu, simply select Register. Then you'll need to let us know what you'd like to receive, in this case, the APA update newsletter. Lastly, APA has field staff located throughout the country. These talented individuals like Alita and Larry are available to assist design professionals, builders, and code officials. Their individual contact information can be found on our website at apawood.org. Please reach out and take advantage of this free resource. And with that, I'd like to thank you for attending. Have a great day.